All right. So hello, everyone. My name is Yujing, and I was a part of the summer 2020 MiCM group. So my supervisor is Dr. Yang Sunjun from the McGill Medical Physics Unit. My topic is multi-branch deep learning framework in head and neck cancer outcome prediction using pre or during treatment data. Okay, so here's a little bit of an introduction. Over 50% of all cancer patients receive radiation therapy during their cancer treatment. However, the prognosis of any individual patient is still poorly determined. Although local regional control of most head and neck cancer is reasonably good, about 90%, long-term survival is quite poor within these patients. They can be as low as 35% depending on the tumor type. This is largely due to the distant metastases development or second primary cancers. Therefore, a model that can accurately discern between high-risk patients and low-risk patients prior to treatment is very crucial. Therefore, so that a better informed decision can be made regarding patient risk stratification. So, for example, a more aggressive treatment regime can be assigned to high-risk patients, potentially enhancing their outcome. In contrast, low-risk patients could consider a more conservative treatment, such as delivering less radiation to reduce harmful side effects such as hormone disorders, dental diseases, and so on. This is an effort towards personalized medicine eventually becoming a reality, to put it into big terms. So in this project, we specifically focus on head and neck cancer patients, 70% of which undergo radiation therapy. Head and neck cancer is a group of neoplasms originating from the squamous cells that line the mucosal surfaces of the oral cavity, paranasal sinuses, pharynx, and larynx. These cancer patients undergoing radiation therapy receive both anatomical CT and metabolic PET-CT imaging. We recognize that from the tremendous amount of data generated by PET-CT and CT imaging when a patient receives cancer care, much of which is currently not systematically used to its full potential. So that is the motivation of our project. So within the past decade, deep learning which is a subfield of machine learning, has been increasingly used for healthcare applications. A convolutional neural network, CNN, is a type of deep learning algorithm biologically inspired by the neural network within the animal visual cortex. So our group actually previously showed that a CNN could be applied directly to a patient's pre-treatment CT imaging data and perform outcome prediction of comparable accuracy to a benchmark study on radiomics, which is another field on the same data set from before. So here, the uniqueness of our proposal is that we propose a multi-branch deep learning architecture where both pre or during treatment PET-CT images and clinical information are introduced to the neural network in addition to the CT imaging branch to predict various clinical endpoints. What I mean by multi-branch is that different forms of input data, so different imaging modalities, can be used here. By clinical endpoints, I specifically mean distant metastasis, local regional failure, and overall survival. So therefore, we hypothesize that the multi-branch deep learning architecture will obtain results superior to the current state-of-the-art models with only pre-treatment CT data incorporated as inputs because we have this multi-branch feature. So let's talk about how the clinical data is obtained in order to train this model. So clinical data of eligible patients from the Varian medical system has been imported. More specifically for the first two data branches, PET-CT and CT data of a patient with either one or two treatment plans will be will so patients with only 1 or 2 treatment plans can be included in the study. And these treatment plans have to be pre or during treatment. These images have to have been taken pre or during the treatment. So image registration is a process that is performed where the contour of the gross tumor volume GTV is copied from the anatomical CT images onto the CT portion of the PET CT images. Then the clinical information branch of our deep learning architecture, including patient anonymous ID, age, treatment plan, dosage, gender, tumor type, tumor location, TNM stage, GTV type, tumor pathology, existence of P16, things like smoking history, total dose prescribed, total dose fraction, total number of dose fraction received, number of dose fractions per plan, treatment start and end dates, and PET CT end dates, and these things are all the sort of clinical branches, the data that was obtained for the training of the model. Okay, so here are some preliminary results that will need further work for the testing data. So here we show we use, for the training and validation set of the study, we use the same data as the benchmark start study, as I mentioned before. These data led to this preliminary results. So the validation set accuracy shows that our multi-branch framework improves model performance for all 3 clinical outcomes. So you see the green bar on the left has a better AUC value than the other combinations, because here we have all 3 branches available, but the other columns here, they have 1 branch or 2 branch, different combination, but less than all 3 branches adding up together. So from this, we can, we basically showed preliminarily with the validation results that having a multi-branch deep learning model will obtain results better than a single branch model, which is pre-treatment CT data compared to our current 3 branches, the PET CT, CT, and clinical information. Okay, so yeah, so currently there still needs some work in terms of finishing with the test set data remotely, and how this model was obtained is that the PET CT and CT data branches will be trained independently prior to being merged with the clinical data branch. The framework is based around a combination of convolutional networks made up by the branches aligned horizontally, followed by a multi-layer perceptual MLP. And using the long test will evaluate the outcome prediction accuracy, improvement statistical significance while computing the AUC, specificity, sensitivity, and balance accuracy to determine the validations and test set accuracy for each clinical outcome endpoint. So that's how these graphs came about. And by the way, we'll do the same for the test results to confirm. So here in conclusion, I want to talk about what's unique about this project. So there is a wealth of literature investigating potential predictive image features that's called radiomics of both image modalities individually, which are PET, CT, and CT, but they have never been combined and investigated together or incorporated clinical information within a deep learning context, such as using a convolutional neural network, CNN. So the novel contributions of this work are fourfold. Firstly, we develop a novel multi-branch deep learning framework capable of incorporating multiple forms of input data to perform accurate outcome prediction on an independent testing set. Secondly, we propose a novel training methodology where each branch of the framework is trained independently prior to combination resulting in a performance improvement. Thirdly, the framework is capable of functioning, albeit at a loss, even if one of the forms of input data is missing, which is a commonly occurring situation within outcome prediction and thus a desirable feature within our predictive model. Finally, this model will effectively and efficiently utilize unused imaging data from radiation therapy. So, and here are the references, and that's about it. Thank you very much for your time and listening, and I was really grateful for the MiCM award this summer, and I want to thank my supervisor, Dr. Yan Sinjin, as well. Yeah, hope everyone is staying healthy, and thank you so much. Bye.